Hi everyone! Today I will present our work on data acquisition to enhance machine learning performance. We start from a common data acquisition setting, given a data pool and a supervised model trained on an initial training set. The goal is to select high-quality data points from the pool to enrich the training set and maximize the performance of the retrained model. For this problem, a state-of-the-art solution is the clustering-based training set selection, or CTS, algorithm. CTS consists of two steps. The first step is data point clustering, which groups similar data points into a set of clusters. The second step is iterative data point selection from clusters. In each iteration, CTS first selects a cluster and samples a mini-batch from it. Then it adds the mini-batch to the current training set and retrains the model. Next, it evaluates the resulting performance improvement. If the observed improvement is negative, the mini-batch is removed from the training set. Finally, CTS updates the reward of each cluster based on the observed improvement and uses these rewards to guide subsequent selection. Despite its merits, CTS still has several limitations. The first is frequent retraining overhead in Operation 2, which is very expensive and accounts for more than 90% of the total runtime. The second is exploitation score marginality in Operation 5. The current exploitation score may not accurately reflect the current cluster state, while the current exploration score relies only on exploration frequency. As a result, the selection guidance may not be sufficiently effective in subsequent iterations. The third is the single cluster sampling bias in Operation 1. If a cluster fails to improve effectiveness, that is, model performance, in one iteration, the consequences may cascade to subsequent iterations. To address these limitations, we propose three optimization techniques. First, for limitation 1, we introduce online learning to improve efficiency. Instead of retraining the model from scratch in each iteration, we incrementally update its learnable parameters with the newly added data points. Second, to address limitation 2, we propose adaptive score estimation by designing a new selection criterion based on an adaptive score. The adaptive exploitation score emphasizes recent rewards by assigning them higher weights so that the current cluster state is more accurately reflected. The adaptive exploration score, in turn, guides exploration efforts to improve the overall effectiveness. Third, to address limitation 3, we propose adaptive mini-batch selection. Rather than sampling from a single cluster, we sample a mini-batch from each cluster. The number of sampled data points from each cluster is determined by its adaptive score relative to the sum of all adaptive scores. By combining these three techniques, we develop two algorithms. The first is IAS, which extends CTS by combining online learning with adaptive score estimation to improve both efficiency and effectiveness. The second is IAS-AMZs, which further incorporates adaptive mini-batch selection to strengthen effectiveness. Using these two algorithms, our experiments show strong improvements in both effectiveness and efficiency. In terms of effectiveness, IAS-AMZ is the best performing method, and IAS also outperforms the other competing algorithms. For example, IAS-AMZ delivers performance improvements of at least 5% in the results shown here. So, if we care more about effectiveness, IAS-AMZ is the preferred choice. For efficiency, IAS achieves the best efficiency. At the same time, IAS-AMZ remains comparable to the existing CTS algorithm in runtime while achieving better effectiveness. Overall, these results show that our methods significantly improve the efficiency-effectiveness trade-off for data acquisition. That's all. Thank you very much.